Our research presenter today is Megan Donahue, professor in the Department of Physics and Astronomy in the College of Natural Science. A graduate of MIT with a bachelor's degree in physics, she went on to earn a PhD in astrophysics from the University of Colorado, where her dissertation won the 1993 Trumpler Award from the Astronomical Society of the Pacific. She next served as a fellow at the Carnegie Observatories and the Space Telescope Science Institute. Since joining MSU in 2003, she has been recognized through a number of awards, including the Beale Outstanding Faculty Award in 2014. Dr. Donahue is a fellow of the American Association for the Advancement of Science and the American Physical Society, and she was just elected president of the American Astronomical Society and will begin her term in June. That society is the main professional society for astronomers in North America. Donahue, along with MSU professor Mark Voigt, are co-authors of the best-selling undergraduate astronomy textbook series, The Cosmic Perspective. Her research centers around cosmology, clusters of galaxies, and galaxy evolution. And if I could just add, because I do some work in this area, physicists and astrophysicists have discovered in the last decades that the type of matter that we're made of, that our sun is made of, and the things that we can see, even in distant galaxies, is only a tiny fraction of all the mass and energy in the universe. In fact, there is some other stuff out there that we still do not understand, and Megan will tell you all about it.
In 5 minutes or less, thank you. So I'm here to give you the very big picture. So you may remember, it was probably a long time ago when you had a view of the full night sky when it was dark, and you saw a few hundred, maybe a few thousand stars. And perhaps you saw a view like this of the Milky Way spanning over the horizon, and we're inside the Milky Way. We're one of those many stars. In the 20th century, we realized that these tiny little smudges in the very distant sky are actually galaxies like our own. The universe is full of these galaxies, and it was through study of these galaxies and their motions that we realized the universe is expanding. It has a finite age, and by detailed study of this expansion, we inferred the presence of some mysterious substances in the universe like dark energy and dark matter. These galaxies are full of stars. This is a small picture of one of our sister galaxies, the Andromeda Galaxy, a galaxy much like our Milky Way. A zoom in, this is stitched together from many hundreds of Hubble Space Telescope pictures. We see the individual stars at the distance of the Milky Way, about 2.5 million light years away. That is, light took 2.5 million years to get there, get here from that galaxy. So what is the universe made out of? And I'm sure you're going to be seeing a lot of budgets today, so I thought I'd give you the universe's mass energy budget. And it's all been translated to the same currency of mass energy. We can do that using Einstein's equation equals mc squared. And we see that a large fraction of the universe is dark energy. This is the cause of the acceleration of the expansion of the universe. There's the stuff that Stephen mentioned, dark matter. There's the gas, and the things that 20th century astronomers have been studying, for several hundred years. The stars represent less than 0.5% of the mass energy budget of the universe. A galaxy's mass budget is slightly different because the dark energy is smoothed out uniformly over the universe, whereas gravity works to clump matter together. So in galaxies, we see the representation of just the matter in the universe. And so it's a slightly different pie chart where still most of that pie chart is represented by dark matter and only a sliver is accounted for by stars. But in a typical galaxy, there's another mass shortage, an audit alert, where we can only account for about 10% of the gas in the galaxy when we look at the total mass budget of a typical galaxy. And here's another picture of the Andromeda Galaxy now. We're seeing the full thing. We see the disk stars. There's a bunch of stars around the center of the galaxy we call a bulge. There's stars in the halo. There's interstellar gas. But the question is, and I almost forgot, there's a central black hole in this inside of nearly every galaxy. That represents a very small percentage of the mass, less than 0.3% of the mass of the galaxy. So the central black hole, though we're going to see it's an important part of the story, is not an important part of the mass. So where is most of this gas? Well, studies by the Hubble Space Telescope and other large ground-based telescopes show us that this is not the entirety of a galaxy. Actually, a galaxy is surrounded by a gaseous halo that we can study through absorption line studies, but it's very, very faint in emission. Most of the gas and heavy elements actually lies in this halo, not inside the stars or even in between the stars, but in this gaseous halo around the galaxies. So if we want to really get a full accounting of the stuff in the universe, the matter in the universe, we have to study the stuff around the stars. There's another mystery in that these central black holes tend to be bigger in bigger galaxies. And that suggests that the central black holes evolves together with the galaxies. So how these black holes interact with the gas around the galaxies provides another clue about the story of how galaxies form and evolve. Here's a picture of one of those central black holes in radio light. This light is invisible to us from optical telescopes, but radio telescopes show that they can have tremendous jets spanning millions of light years across, shooting out into what looks like empty space, but is clearly impacting on something out there in the halo around galaxies. So here at MSU, we study that gas by looking at the gas where it really lights up. In the most massive galaxies in the universe, the high temperature of that gas allows us to study it in X-ray light. So this is an X-ray telescope picture of a cluster of galaxies. Here's the central galaxy here, but you see this incredible halo of gas, and we can only see it by studying it in the X-rays. Oops. All right. So we need multiple telescopes to get a full picture of the gas and stars in a cluster of galaxies or in a galaxy. So we use the Chandra X-ray telescope, the Hubble Space Telescope to study things in the ultraviolet and the optical, the VLA to study things in the radio. And you see a galaxy looks very different at all those wavelengths. So this is a composite picture of X-ray light, optical light. This is the radio image of the central galaxy in the Perseus cluster. That's showing that radio plasma is excavating cavities and shock waves in the surrounding gas. The optical light shows where the stars are. So at Michigan State University, we use these telescopes and computer simulations of galaxies to study the relationship between that central black hole, the circumgalactic gas, and the central galaxy to construct a narrative of how galaxies evolve. One important tool at Michigan State is the SOAR telescope, which MSU invested in the late 90s and continues to contribute operating costs. And we use the SOAR telescope together with telescopes, orbiting NASA telescopes like Chandra, to study this gas and study this question and assemble the story of galaxy evolution. And I'll just leave my closing slide up there for you. Thank you.
The universe has a finite life to it.
Right.
Did you?
Yes.
So
Yes, it is.
can you just? So what? So it's going to go. Does the universe in your theories and all that have an end to it? A border?
Well, that's a great question. And so one of the aims of cosmology is to answer that question. We think, but we don't know, that the universe will continue to expand forever. And especially since there's not enough matter to slow that expansion, matter pulls, just like when you throw a ball into the air, there's enough matter here to pull that ball back to the Earth. But if I launch that ball fast enough, it escapes the Earth's gravity and will continue out into space forever. So one of the questions of 20th and 21st century cosmology is whether there's enough speed in that expansion to escape the gravity of the universe. And apparently there is, especially with the assistance of this dark energy, which seems to be accelerating the expansion. And that is as counterintuitive, as if you tossed a ball into the air and then it just launched itself and accelerates out. So that was completely a completely unexpected aspect of studying the expansion of the universe in cosmology, because cosmologists fully expected that expansion to at least be slowing down, not necessarily to reverse, because you need a lot of matter to reverse it, but to be slowing down. And they were astonished to find it was accelerating, and that became the subject of the Nobel Prize in 2013. So several of my friends got the Nobel Prize and tickets to the Ravens. And
Right.
Okay,
Okay.
thanks.
Questions? Other questions? I'm going to put both of you on the spot a bit. This is very, very fundamental and important research. And universities, this is what universities do. If we were having this conversation 5, 10, 20 years from now, and we were trying to think about what this might mean to people in their day-to-day lives, is there an answer to that question?
well, I get no shortage of just natural human curiosity in the answer to the question, where did we come from and where are we going? And so I think those sort of fundamental questions just don't go away, even if I'm trying to pay my water bill.
Steve, you want to add to that?
I think all of us are interested in these fundamental questions. You can see that in Brian's very first response to this. So these are questions that humans have been asking themselves since the beginning of our civilization, and it's amazing that we have some answers, that there appears to have been a Big Bang in the past, and it appears that the expansion of the universe is actually accelerating, which was a huge surprise, as Megan said. In terms of applications, this is not the area that necessarily is going to produce applications. However, for example, the computation that astrophysicists have to use today to process all the data that they get puts them typically at the leading edge in areas like statistics and machine learning and computation. So it does tend to have spin-offs. And if you ask Megan where her former postdocs and graduate students work, probably a number of them work at Google or other organizations like that.
That was I think we sometimes look at the science as only what is the curiosity, and not all of the infrastructure that's around the science, and the implications of that development of infrastructure for talent. Google, big data, data learning, machine learning, all those things are required in enormous ways to take what is Earth observations, telescope observations, calculations, and then make them a part of what translates into our lives, not as the answer to a question of curiosity, but an enormous benefit to society that comes from all of those ancillary things that you have to have in order to pursue a very fundamental question. And that's part of why I think it's important for us to remember that. And this presentation is a really good example of why people might look at this and say, this might be unnecessary. But without this, all those Google things, all those big data things, all those information that we're now using in different ways would not have been driven by the curiosity. Is that a fair?
I would add to that, when I talk to the tech organizations, or I talk to the folks who build these telescopes or these rockets, this is a small piece of what they do for the U.S. government and so forth, and it is part of their entire enterprise. So this is what excites children to go into science, and so I think that's a very important aspect as well.
No, I agree. There's excitement, curiosity, there's the knowing and better knowing, and then there's the spin-off because of the way in which you know. Is that
And if we're ever going to get off this planet, it's because we're going to be chasing that.
Megan, could you please take a moment and explain MSU's investment in the SOAR telescope?
I don't have all the numbers at my fingertips. A lot of this happened before I arrived. But MSU purchased a share. It's a 15% share in a 4-meter telescope in Chile. We have an observation room in the Biomedical and Physical Sciences building. That is amazing. I don't have to travel 48 hours there and back to have 2 nights of observing. I can have a tea and walk down to the observation room and talk to the telescope operators and control the instruments from here. in East Lansing, and it's a world-class telescope. It's amazing instrumentation, and I can combine the data sets that I get from that telescope with data sets from the Hubble Space Telescope or Chandra X-ray Telescope. Those are in orbit. So I do a lot of NASA work. It leverages a lot of resources in our direction. So most of our funding, I would say, comes from NASA.
Thank you.
That's my whole research program.
Paul, do you want to add it? Paul and Steve. Paul Hunt was in a former role, and I guess Wolfgang, you may have been chair of the department, and I can't remember. You were chair of the physics and astronomy
On the
department.
front line.
And Paul was the person who, through the provost office, was worrying about telescopes. So Paul, you may want to.
To Trustee Foster's question, the SOAR telescope is a consortium between MSU, the University of North Carolina, and Chapel Hill, NOAO, which is an NSF-funded National Optical and Astronomical Observatory, and CNPQ, which is the country of Brazil's NSF equivalent. The Board of Trustees, in the date range that Megan alluded to, approved a $6 million capital investment in what was about a $28 million total project. And under that deal, the folks at NOAO, who were not major capital partners, agreed to operate the telescope for a period of time thereafter. We're in that operating window now, so our annual expense on SOAR is small currently, although eventually that operating period will end and we'll have to revisit it. But Megan and her colleagues have made a number of very interesting contributions using SOAR over the time. So I think from the Vice President for Research Office perspective, the investment has been well worthwhile, not only in terms of the science produced, but also the recruitment effects with Megan and her colleagues.
And also, they do a number of programs for families and children, because the observatory room is on the first level of biophysical sciences. And so it's an opportunity for people who might not ever experience an observatory of this type and magnitude in science to get excited about science. And you do a lot of
Right.
kids'
We
programs.
invite students to come by anytime they want, and I can bring several graduate students, including junior students. You know, the trip to Chile is about $1,500 per person, so it is quite a great
Yeah.
investment in remote observing. Yep.
Thanks, Megan.
Yep. Thank you.
We're pleased to have you.
Thank you.